Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. In this exercise, we're going to find the area between a parabola and a straight line using polar coordinates and a double integral. I'll demonstrate how to formulate the double integral, and if you stick around until the end of the video, which I hope you will, I'll show you how to evaluate the double integral. Suppose then we have a parabola with equation y equals x squared and a straight line with equation y equals x. When the line intersects with the parabola, a region is created between the two shown here in red. We're tasked with finding the area of this region. The first step in finding the area is to convert the equation of the parabola and the straight line from Cartesian to polar coordinates. To do this, we'll substitute r cos theta for x and r sin theta for y. The equation of the parabola in Cartesian coordinates is y equals x squared, and making the substitution gives r sin theta is equal to r squared cos squared theta. Dividing both sides of the equation by r and cos squared theta leaves r equals sin theta divided by cos squared theta. The straight line in Cartesian coordinates is y equals x, and making the substitution for y and x we get r sin theta is equal to r cos theta. Dividing both sides of the equation by r and cos theta gives sin theta divided by cos theta is equal to 1. And using the trig identity where sin theta divided by cos theta is equal to tan theta, we're left with tan theta is equal to 1. And therefore theta is equal to pi by 4 radians. Now that we've made the conversion from Cartesian to polar coordinates, let's look at the behavior of the radial distance r as we use it to compute the region shown in red. As r rotates in a counterclockwise direction from theta equals 0 to theta equals pi by 4 radians, theta being the angle r makes with the x-axis, the radial distance from the origin is determined by the parabola. When the parabola intersects with the straight line at theta equals pi by 4 radians, the area is complete. We are now in a position to start defining the limits of integration as r rotates about theta, which will be the outer integral. The area of our region R can be defined as a double integral over the region R, where we sum infinitesimally small pieces of area shown as dA. In this case, the region, as we saw, extended from theta equals 0 to theta equals pi by 4 radians. These become the limits of the outer integral. Now let's look at what happens when we sum infinitesimally small pieces of area along the radial distance r, or in the r direction. This will help us define the inner integral. When we integrate in the r direction, this will represent the inner of the two integrals. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each area is the length multiplied by the width. So in this case, dr is the length and r d theta the width. So dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. When we sum or integrate along the radial distance r, we begin at the origin and travel along the parabola until it intersects with the straight line. So we begin at r equals 0 and end at r equals sin theta divided by cos squared theta. Now we're in a position to add the limit of integration when we integrate or sum along the radial distance r. We saw that our lower limit was at r equals 0 and our upper limit at r equals sin theta divided by cos squared theta. And we saw that we are summing infinitesimally small pieces of area denoted by dA, which translates to r dr d theta. We can now start to evaluate the integrals. Beginning with the inner integral, we have the integral from r equals 0 to r equals sine theta divided by cos squared theta of r dr. And the antiderivative of this is r squared divided by 2. And plugging the limits of integration in, we get sine squared theta divided by 2 cos to the power of 4 theta minus 0, which equals sine squared theta divided by 2 multiplied by cos to the power of 4 theta. And now working on the outer integral, we want to integrate between theta equals 0 and theta equals pi by 4 radians, sine squared theta divided by 2 multiplied by cos to the power of 4 theta d theta. And the antiderivative of this is tan cubed theta divided by 6. Plugging in the limits of integration, we have 1/6 minus 0, which equals 1/6. So we now have our final solution, where the area of the region shown in red is equal to 1/6.